All right, so I got cut off again. We were working on this problem here. We were trying to find the equivalence point, the pH at the equivalence point for this titration, where we have a weak acid and a strong base. All right, so what happens is the volume, to figure out the volume, it's the same. We're still using this equation here. So the volume of acid times the volume, or times the concentration of the acid, molarity of the base times the concentration of the base. And we solved in the previous lecture that this was 25 milliliters of NaOH. All right, so when we add 25 milliliters of NaOH, we are neutralizing all of that weak acid. Okay, so the moles of our acid equals the moles of our base, and that number of moles, either way, is 0.0025 moles. Okay, but when we neutralize the moles of that weak acid, all right, so that HCHO2, all right, when we neutralize it, it's like we are subtracting 0.0025 moles of this. And since this is an equilibrium with its conjugate base, all right, we are adding 0.0025 moles of this. So although we completely neutralize the acid with the base that we add, what we end up with is actually a little bit of base. All right, so to figure out the pH at this point, we need to figure out what the concentration is at the equilibrium, making an icebox for this equation. So we have, at this point, we have 0.0025 moles of this weak base, and we have a total volume of our acid we had 25 milliliters of acid. And we also added 25 milliliters of base. So we have a total volume now of 50 milliliters. So when we're doing an icebox, we're going to want the concentration. So I'm just going to go ahead and convert this to concentration. We have 0.0025 moles in a total volume of 0.050 liters. So that concentration is 0.05 molar. All right, so we have 0.05 molar of this conjugate base. So what we need to do is write out the equation so we can do an icebox and figure out the pH. So this conjugate base is in equilibrium, or I should say it reacts with water to form the conjugate acid, HCHO2, and hydroxide. And we just calculated that the concentration of this base that we have at the equivalence point is 0.05 molar. We don't care about water. This is 0. So this is going to go down by some amount, and these are going to go up by some amount, and we'll end up with some final equilibrium concentration of this hydroxide, which is going to make this, at the equivalence point, a little bit basic. So this will be 0.5 minus X. The Kb for CHO2 minus is 5.6 times 10 to the negative fourth. So we plug in our equilibrium concentration, or equilibrium expression, 5.6 times 10 to the negative fourth equals the concentration of the products, X times X, which is X squared, divided by the concentration of the reactants, 0.5 minus X. We're going to assume that this X is small enough. And we are going to do the math here. 0.05 times 0.05. And then we will take the square root of both sides. And we get that X equals 1.67 times 10 to the negative 6. And we should do a validity check, which I did not do in my notes, but I'll do real quickly right now. 1.67 EE negative 6 divided by our initial concentration of 0.05 times 100. I think I did that wrong. 1.67 EE negative 6 divided by 0.05 times 100 is still less than 1%. So it's less than 1% of the initial concentration. So this checks out. So this is X, X being our concentration of hydroxide. So we just figured out that the concentration of hydroxide is 1.67 times 10 to the negative 6. So the POH is the negative log of that. And the negative log of 1.67 times 10 to the negative 6 is 5.78. So the pH will be 14 minus 5.78, which is 8.22. So the pH at the equivalence point, in this case, is, here's the buffer region, here's the equivalence point. The pH is going to be 8.22. So at the equivalence point, the pH is greater than 7 for a weak acid titrated with a strong base. All right, so then the last part of that curve, the top part, so here's the buffer range, here's the equivalence point that's greater than 7, and then here's the excess titrant point up here. So if we wanted to find the pH at some point up here, beyond the equivalence point, all right, then that hydroxide ion from the added base, in this case the volume of OH, is on this x-axis here, all right? So all we have to do is calculate how much excess OH we have by doing some subtraction, some mole subtraction, which is the same way we did it for the strong acid, strong base. So this region of the graph is calculated the same as for how we did it before. So if we have an example problem, calculate the pH after adding 40 milliliters of sodium hydroxide. All right, and remember we calculated that this equivalence point was at 25 milliliters. So 40 milliliters is in fact up here beyond the equivalence point. So at the, we keep calculating the moles of acid, which is constant because we're not changing the amount in that flask. So we have 0.0025 moles of acid. And how many moles of base did we add? If we have 0.1 molar or moles per liter, and we add 40 milliliters or 0.04 liters, then that's 0.004 moles of hydroxide. So that means that we can neutralize all of this acid and we'll have left over we will have a leftover amount of 0.0015 moles of hydroxide. And if we want to find the pH or the POH, we always need to know the concentration. So the volume, the total volume that we have at this point is our 25 milliliters of acid plus those 40 milliliters of base for a total of 65 milliliters. So to turn this into a concentration, we just divide it by that volume, 0.065 liters. And that gives us a concentration of 0.023 molar, and that's our concentration of hydroxide ions. So if we have a concentration of hydroxide, we can find the POH. That's going to be the negative log of 0.023, which is 1.64. And then we can derive the pH, because that's just going to be 14 minus 1.64, which is 12.36, which is very basic, which is what we expect up here. We have an excess of base. Okay, so these can be long problems when they have multiple parts like this. We're going to work one of these together. Or you can pause and try this yourself. So in this case, we have a weak acid, HNO2, and I'm going to change these values because I did the math and realized that our X approximation technique will not work at those concentrations. So we're going to change this to 1.00 molar and 2.00 molar. Okay, so the first thing we want to do is calculate the initial pH. So part A. The initial pH is going to be of the acid, because we have 40 milliliters of this acid. It's a weak acid, so since it's a weak acid, in order to calculate the pH of a weak acid, we need to use an icebox. So we're going to set up our icebox here. The Ka for this acid we can look up on a table is 4.5 times 10 to the negative 4. And our icebox, ICE, our initial concentration of this is 1.00 molar. It's going to go down by X. These will each go up by X. And so this will be 1 minus X, X, and X at equilibrium. So if we plug this into our equilibrium constant expression, 4.5 times 10 to the negative 4 equals the products, X times X, divided by the reactants, 1 minus X. We'll use the X approximation technique and assume that this X is so small that 1 minus X still equals 1. And we will multiply both sides by 1, which we don't really need to do, so I guess we can take the square root of each side. And we get that X equals 0.0212. And now to just do a quick check, 0.0212 divided by 1 times 100 is 2.12%. So that checks out, it's less than 5%. So our X approximation technique was valid. So in this case, the concentration of H plus is X, which is 0.0212. So the pH initially is the negative log of 0.0212, which is 1.67. The initial pH is 1.67. All right, part B. What is the volume of potassium hydroxide that's needed to reach the equilibrium point? So that is always going to be this equation here. The concentration or the molarity of the acid times the volume of the acid equals the molarity of the base times the volume of the base. All right, the molarity of our acid is 1.00 molar times 40 milliliters equals the molarity of the base, 2.00 molar, and times the volume of the base, which we're solving for. So we just divide both sides by 2.00 molar. This cancels out. And 40 divided by 2 is 20. So the math is, you can do that in your head there. So the volume that we need to reach the equilibrium or the equivalence point is 20 milliliters. Technically it's 20.0. We should have 3 sig figs. All right. Part C is to calculate the pH at the equivalence point. Well, at the equivalence point, all right, we are going to neutralize all the moles of the HNO2 and we'll convert it all to NO2 minus. All right, so at the equivalence point, so how many moles do we have of the acid? We have, and that's going to be the moles of the acid times the volume of the acid. And we have the molarity of the acid is 1.00 times the volume is 0.04 liters. So we get 0.04 moles of the acid. So in other words, we're neutralizing, we're going to, if we sort of do this as sort of a part of an icebox, the change here, we're neutralizing, getting rid of 0.004 moles of this, which means that we're going to be gaining 0.04 moles of this conjugate acid. And so at the equivalence point, we will have 0.04 moles of this conjugate base, the NO2 minus, and it's going to cause this solution to be slightly basic. So we need to do an icebox for this conjugate base. This NO2 minus plus water reacts to form HNO2 and OH minus. We need to figure out the concentration of this OH minus. So to plug into this icebox, we need concentrations. So the 0.04 moles, we need to divide that by the total liters that we have. And at the equivalence point, we had 40 milliliters of acid plus the 20 milliliters of the base, so that's a total of 60 milliliters, so 0.06. So this concentration here is 0.667 molar. So we can plug that in. We have 0.667 molar of this base. Don't care about water. This is going to go down by x. This will go up by x in this equilibrium. So 0.667 minus x, x, and x. All right, the Kb for this base, if we look it up, is 2.2 times 10 to the negative 11th. So the Kb, 2.2 times 10 to the negative 11th, equals x squared over 0.667 minus x. This is a super small Kb, so this x is certainly going to be negligible. We multiply both sides by 0.667. And then we take the square root of both sides, and we solve that x equals 3.83 times 10 to the negative 6. I do a validity check, and I find that this is indeed way less than 5%, so that's good. So this means that our concentration of OH minus at this equivalence point is 3.83 times 10 to the negative 6. The POH would be the negative log of that, so the POH would be 5.42, and the pH would simply be 14 minus 5.42, which is 8.58, a slightly basic pH, which is what we expect for this weak acid strong base. 8.58 is the pH at the equivalence point. We expect it to be greater than 7, and it is. Now, I'm going to need to erase, sorry I didn't leave enough space on here to do all these problems, to do parts D, E, and F. Do some erasing, la-di-da-di-da. Scratchy, scratchy, scratchy. Alrighty, now I've got some more room. Part D, the pH after adding 8.5 milliliters of potassium hydroxide. Okay, so the equivalence point is at 20 milliliters. So if we're only adding 8.5, that's before the equivalence point. And remember, when we have a weak acid, anything before that equivalence point, here's the equivalence point, anything before that is in the buffer range. So for part D, adding 8.5 milliliters, that's going to be in the buffer range. So that means we need to use the Henderson-Hasselbalch equation, which is this, pKa plus log of the concentration of the base over the concentration of the acid. All right, so the first thing we should do is go ahead and find the pKa. All right, and the Ka that we saw before for this reaction is the negative log of that Ka, which was for this weak base, was 4.5 times 10 to the negative 4. So the pKa is 3.35. Cool, so we have that. Now we need to figure out the concentration of the acid and the base. And what we're talking about here, the concentration of the acid, our weak acid, and its conjugate base. All right, that's what we need the concentrations of. So the concentration of the acid, we need to figure out how much we've neutralized. So the total moles initially, the moles of HNO2 that we have, are the molarity, which is 1.0 moles per liter, times the volume in liters. 40 milliliters is 0.4 liters. So as we had calculated before, we initially have 0.04 moles of the acid, and when we add our potassium hydroxide, the moles of potassium hydroxide, it's 2.00 moles per liter, and we're adding 8.5 milliliters, which is 0.0085 liters. So that is a total of I did my math wrong. So that is 2 times 0.0085, 0.017 moles. All right, so that means we need to subtract that. So the moles of HNO2 that we have at this point is 0.04 minus 0.017 moles, is 0.023 moles of our HNO2. All right, and for every mole of acid that we neutralize, we make that many moles of base. All right, so that's how many moles of base we have, of the conjugate base, and this is how many moles of the conjugate acid. But we need to figure out concentration. Remember, brackets are concentration. So the total volume that we have at this point, we have a set volume of 40 milliliters of acid. We've added 8.5 milliliters of our titrant base. So now we have 48.5 milliliters total volume, which is equal to 0.0485 liters. This is definitely the longest step of this reaction, of this problem. Okay, so our concentration of acid, HNO2, is 0.023 divided by 0.0485 moles per liter. 0.023 divided by 0.0485 equals 0.474 molar, and the concentration of the NO2 minus is 0.017 moles per 0.0485 liters. 0.017 divided by 0.0485, 0.351 molar. Now we have all the information that we need to plug into that Henderson-Hasselbalch equation. pH equals pKa. The pKa we said was 3.35 plus the log of the concentration of the base, which is 0.351, over the concentration of the acid, 0.474. And so that simplifies to 3.35 plus, let me just calculate this log real quick, 0.351 divided by 0.474 is 0.741, and the log of that is negative, so it's negative. So 3.35 minus 0.1305. So the pH equals 3.22. All right, the pH after adding 8.5 is 3.22. So it goes up a bit. But it's not quite, of course, to the equivalence point. And then for E is much shorter. Do I have any room for E? I do. All right, so E is what is the pH after we've added 30.5 milliliters of KOH. So we already just calculated that the total number of moles of acid that we have, all right, is 0.04 moles. All right, so how many moles are we adding when we put 30.5 mils? So it's 2.0 moles per liter times 0.0305 liters. I don't know why these are weird numbers. And so when we add that many moles, we get 0.061 moles of our base, okay? So we're going to neutralize all of that acid and we're going to have excess base. So 0.61 minus 0.04 equals 0.021 moles of excess hydroxide from adding that many moles of base. So we can find the POH, we can find this, we can turn this into a concentration because our volume at this point is 40 milliliters of acid plus 30.5 milliliters of the base. It's a total of 70.5 milliliters. So 0.0705 liters gives us the concentration of hydroxide, which is 0.298 molar. So the POH is the negative log of that, which comes out to be 0.53. So the pH at this point is 14 minus 0.53, which is 13.47. So we can write that in up here, 13.47. And we can sketch this out, all right, or we can complete this sketch here, simply labeling it. We can say that the initial pH was 1.67. This is our pH scale. And that at that equivalence point, it was 8.58. And that up here, once we had added 30.5 milliliters, the pH was 13.47. And then we could also add that this point here was at 20 milliliters. The equivalence point was reached at 20 milliliters of our base. So that's sort of a sketch. The important thing with sketching this curve is making sure you have that little buffer curve here, that it's not a straight line like we see with the strong acid, strong base titration. So the last little bit of information in this chapter to talk about our pH indicators, which we're going to be using in the titration lab. So an indicator, or a pH indicator more specifically, it's an organic molecule that when it is when acid or base is added, it changes its color. And there's a lot of these. They're usually plant pigments. And so the equilibrium of these things looks something like this. The indicator, when it's protonated, when it's an acid, it's, some color. Let's say it's blue. All right. But then when you change the pH and you have the indicator in its conjugate base form, it's some other color. Okay. So by manipulating this equilibrium, by adding acid, you would shift it this way and it would become blue. And if you subtract acid by adding base, then you'd shift the equilibrium this way and turn it green. So when the pH of a solution is equal to the pKa of the indicator, you get sometimes an intermediate color. But when the pH of the solution is greater than 1 of the pKa of that indicator, then you get the color on this side, and in the other situation, you get the color of this. So there's a bunch of different indicators.